Okay, I need to go back and clarify and actually correct something I said on my last video. So let's take a look here. Everything I said before works just fine for all the geometries we talked about except for spherical geometry. And it's when you get to this, we get to the bounded metric that we run into some weird properties of distance that we have. Distance and between and coordinates that we need to be a little bit careful about. So no change to what we said here. Another name for antipodal points or polar opposite points. So I added that. Everything's the same here. We talk about between. We can use between then to define line segments and array. And once we get to array, then here's how we're going to do a coordinate system to make this thing work. We're going to do a coordinate system for array and postulate that such a coordinate system exists. This is going to clean up a little bit of the problems that we have the way I did it in the last video. So a coordinate system for array AB is a one-to-one correspondence F between the array AB. Okay. And a subset of the real number C such that okay, I need to switch a couple of notations here. First of all, that the f of A is 0, so the coordinate of the endpoint is 0. For any 2 points, I'm using C for something else. Let's say D and E on the line. Then the distance from D to E is f of E minus f of D. Okay. So everything that works just the same as we had it. And if the distance metric is unbounded, that set C as the non-negative real numbers from 0 to infinity, including 0. If it's bounded with least upper bound U, then C needs to go from 0 to U inclusive. So this assigns coordinates between either 0 to all the way to infinity for the unbounded cases. So that's like Euclidean geometry, taxicab geometry, hyperbolic geometry. But for the bounded metric, spherical geometry, you're going to give it a number between 0 and pi for spherical geometry. U is pi. So the output of the function is known as the coordinate of the input. The point with coordinate 0 is said to be the origin of the coordinate system, which of course will be the endpoint. So then the ruler postulate now says there exists a distance metric for this geometry, and every ray has a coordinate system. So here's a ray with a coordinate system in Euclidean geometry. It goes on forever to the right. I've got at least some of the points labeled here. Now, then we'll make a definition for a coordinate system for a line as well. Given any 2 points A and B, a coordinate system for the line AB is a one-to-one correspondence between, we'll go ahead and say line AB, and points of the line between, let's see, actually I'm going to take that out. Between the points of line AB and a subset S of the real numbers, such that the distance metric is unbounded. Then given any 2 points, C and D on AB, we have DC equals G of D minus G of C, and S equals the entire set of real numbers from negative infinity to infinity. Okay. All right. So that's the unbounded case. And if the distance metric is bounded with least upper bound U, okay, then we have that CD is G of D minus G of C if and only if that distance is less than or equal to U. If it's bigger than U, and this should say greater than here. So if it's greater than U, then it's 2U minus that difference, the absolute value of that difference. Okay, and we'll examine this a little more closely in a later video about how these properties of betweenness sort of play out in each of the geometries, particularly how some of the weird things that happen in spherical geometry that you have to be very careful about. Okay, so proposition 11 now is, we'll call it the linear coordinate theorem. Given any two distinct points A and B, there exists a coordinate system G, the function G, for line AB with G of A is 0 and G of B equals the distance AB. And so the linear coordinate theorem then says that any line can be thought of as a number line, and a Euclidean number line, of course, is going to go forever. It's unbounded, and it's going to go all the way from negative infinity to infinity on the coordinates. And of course, in this case, we call, let me go ahead and say that. In this case, we call A the origin of this coordinate system. Okay, so that clears up actually some mistakes that were made in the last video on the part of how this coordinate system works with basically spherical geometry. Everything I said in the last video is completely fine for the other three geometries, but for spherical geometry we need to make these corrections to make things work. Okay, we'll talk a little bit more about this in some later videos as well.